Hi, this is the video of the paper Datalog-Expressibility for Monadic and guarded second-order logic at ICALP Conference 2021. This is joint work of Manuel Bodirsky, Sebastian Rudolph and myself, Simon Knäuer. In our paper, and also in this video, we investigate the intersection of two formalisms that are intensively studied in theoretical computer science, namely Monadic second-order logic and Datalog. Let me start by introducing those two formalisms.
Monadic second-order logic is a well-known fragment of second-order logic. A remarkable point in the study of MSO is probably Büchi's theorem from 1960. In the theorem, Büchi showed that the formal languages that can be defined by MSO are precisely those languages that are regular. A second important theorem about MSO is Cosell's theorem from 1990, which states that there exists a linear time algorithm that decides MSO properties on graphs of bounded tree width. On the other hand, we consider Datalog. Datalog is known as Prolog without function symbols, or as the class of local consistency algorithms. Furthermore, Datalog is a common query language in database theory and, as well as MSO, a fragment of second-order logic. So since both formalisms, Datalog and MSO, have some nice computational properties, one could wish to have a combination of them. And this raises the question that motivates our paper, namely which computational problems are at the same time in MSO and can be solved by a Datalog program. The contributions of our work are a description of the intersection of MSO and Datalog in terms of constraint satisfaction problems. This description can be used as a necessary condition for the question whether the accepted language of a given Datalog program is definable in monadic second-order logic. In our paper, we additionally give a characterization of the intersection of MSO and Datalog by pebble games. But this will not be part of this video here. The last thing I want to mention is guarded second-order logic. Guarded second-order logic is a proper extension of MSO. And all results in our paper also hold for GSO instead of MSO. But for a better presentation, I will focus in this video only on MSO. Let's start by defining monadic second-order logic. Consider a finite relational signature tau. This is simply a finite set of symbols, such that each symbol has an associated natural number, called the arity. Second-order logic is the extension of first-order logic by quantification over relations. This means it is allowed to existentially and universally quantify over relational symbols. Monadic second-order logic now is the restriction of second-order logic, where we require that all quantified relations are unary, have arity 1. If we talk about monadic second-order tau sentences, we mean that all first-order variables are quantified and the tau symbols are not quantified. To illustrate what we mean by this, look at the following example of a monadic second-order E sentence. The only quantified relational symbol is R, which stands for an unary relation here. You can see that all first-order variables are quantified and that the signature symbol E is not quantified. Let phi be an MSO tau sentence. We denote by this phi in brackets the class of all finite tau structures A that satisfy the sentence phi. Consider the MSO E sentence phi from the slide before. What does this sentence mean? It says that for all unary relations R, that are non-empty, there exists an element x in the relation R such that x has no incoming edge from any other element from R. In order to see which structures satisfy this sentence, we look at an example that does not satisfy this sentence. You can see that a set of red nodes forms an example of an unary relation R for which the sentence does not hold. Clearly, the set of red nodes is non-empty. But of course, each red node has an incoming edge from another red node. You can easily observe that the reason for this is the existence of a directed cycle on the red nodes. And this is not a coincidence. The class of finite models of phi are precisely the directed graphs that do not contain such a cycle. The second concept I would like to explain is Datalog. In order to define Datalog, we start with two sets of relational symbols, called EDBs tau and IDBs rho. We assume that tau and rho are disjoint and that rho contains a symbol false of arity 0. Now a Datalog rule is a term psi0 on the left side and psi1 to psi(n) on the right side, where psi0 is an atomic rho formula and psi1 to psi(n) are either atomic tau formulas or atomic rho formulas. And now a Datalog program is nothing else than a set of Datalog rules. What does this mean? What are instances of structures that are accepted by a Datalog program? The semantics of Datalog is as follows. A Datalog program pi rejects an instance if the predicate false can be derived by iterative application of the Datalog rules. If the derivation of false is not possible, pi accepts the instance. Similar to the notion for MSO, we denote by pi in brackets the class of all accepted instances of the Datalog program pi. In order to make this definition clearer, we consider again an example. Consider the following Datalog program pi successor with one EDB successor and four IDBs L, S, T and false. This Datalog program is given by the set of Datalog rules that you can see here. Let's look whether a given instance J is accepted by this Datalog program. In order to see this, we apply the Datalog rules on this instance. Okay, we start by applying the first rule, which says that all tuples in the successor relation are also in the relation S. Now we can apply, for example, the fourth rule, which says that whenever there exist x, x prime, y prime, such that there is an S edge from x to x prime and an S edge from x to y prime, then there is also an L edge between x prime and y prime. Now we can apply the third rule, which says whenever there are x, y and x prime such that L of x and y holds and S of x and x prime holds, then we can add a new S relation from y to x prime. And we can continue like this, again applying the fourth rule, then again the third rule, again the fourth rule, again the third rule. Now we can apply the first rule of the second column, which says that every S edge is also a T edge. After this, we can apply the second rule of the second column, which says that T is transitive. But if we did this, we get a loop at the top element of our instance. And now the last rule of the second column says that we derive false. Therefore, we can say that the Datalog program PySuccessor derives false on the instance j. It's not so hard to see that the accepted instances of the Datalog program PySuccessor are exactly those structures where for every cycle the number of traversed forward edges is equal to the number of traversed backward edges. And of course, this is independent from the direction in which you traverse the cycle in the structure. In our results, we make heavily use of an important observation about Datalog. To explain this, consider this small Datalog program Py and an instance j. We apply the Datalog program Py on the instance j. And we see that all edges are in the R relation. The R relation is transitive, therefore we get a loop, and therefore the Datalog program Py derives false on j. Now consider another instance k, such that j has an homomorphism to k. Now if we apply the Datalog program Py on k, it's easy to see that we can derive false in the very same way as we did on j. This means if there is a way to derive false on j, then there is clearly also a way to derive false on k. Or in other words, if k is an accepted instance, then also j is clearly an accepted instance. This is a general observation about Datalog. Let C be any class of accepted instances of a Datalog program. And let A and B be structures where B is an accepted instance of the Datalog program and A has an homomorphism to B. Then A is also an accepted instance of the given Datalog program. We say that the class C is closed under inverse homomorphisms. With this notion of closure under inverse homomorphisms, I can state our first result. Consider an MSO sentence phi, such that the class of finite models of phi is closed under inverse homomorphisms. Then this class is a finite union of MSO definable constraint satisfaction problems. But what's a constraint satisfaction problem? We make a small digression to CSPs. First, the definition. Let D be an arbitrary tau structure, then the CSP of D is the class of all finite tau structures that have an homomorphism to D. We denote this class by CSP of D. Let's look at the following two examples of CSPs. First, we consider the rational numbers with the order. Then the CSP of this structure is precisely the class of all digraphs that are finite and without a cycle. Another example are the integers with the successor relation. The CSP of this structure is exactly the class of accepted instances of the Datalog program PySuccessor that we already have seen. Now, one could ask which classes of structures are the CSP of some tau structure D. And the following proposition answers this question. A class of tau structures is a CSP for some concrete structure if this class is closed under inverse homomorphisms and closed under disjoint unions. This means whenever A and B are in the class C, then the disjoint union of A and B is also in C. to see the power of our result 1, we consider another example and keep this knowledge about CSPs in mind. Let B, R, and E be relational symbols, where B and R are unary and E is binary. We have the following Datalog program pi. Now we claim that the class of accepted instances of the Datalog program pi is not MSO definable. We consider an instance, which is the disjoint union of two paths not of the same length. If we apply the Datalog program pi, we get that the two blue nodes are connected by the dotted L edge. Further rule application derives false since a red node is L connected to a node that has an outgoing E edge. Therefore, this instance is not an yes instance of the Datalog program pi. On the other hand, if we just consider a path starting with a blue node and ending with a red node, this is clearly accepted by the Datalog program. And this also holds for longer paths. In fact, it holds for all finite paths of this kind. This leads to the following observation. There exists an infinite set X of yes instances, namely all paths starting with a blue node ending with a red node, such that for all distinct elements of this set X, the disjoint union of them is not accepted. This immediately implies that the yes instances cannot be a finite union of constraint satisfaction problems. Because if it would be a finite union of CSPs, one of those CSPs clearly would contain at least two members of X. But this is not possible, since X is not closed under disjoint unions and CSPs are closed under disjoint unions. By our observations from before, the class of yes instances of a Datalog program is closed under inverse homomorphisms. Therefore, we can apply our result 1 and get that the class of all yes instances of the program pi cannot be defined by an MSO sentence phi. In our second result, we go one step further and consider an MSO sentence phi such that the class of finite models of phi is closed under disjoint unions and closed under inverse homomorphisms. Then we get that this class is the CSP of an omega categorical structure. A structure is called omega categorical if all countable models of the first order theory of the structure are isomorphic to the structure itself. Since omega categorical structures have many nice properties, they play an important role in model theory. And also they are a central object in the study of CSPs by universal algebra. A very famous example of an omega categorical structure is the rationals with the order. Why is this omega categorical? By a well-known result of Cantor, there exists up to isomorphism only one countable dense linear order without endpoints. This property, being dense linear order without endpoints, can be expressed in first-order logic. So this is the argument why Q with the order is an omega categorical structure. I want to remark something here. This second result can be used to characterize the intersection of MSO and Datalog in terms of existential pebble games. You can find the details of that in our paper. Similarly, as for result 1, I would like to show you how this second result can be applied to concrete questions about Datalog and MSO. We consider the Datalog program pi successor that we already have seen. We claim that the class of yes instances of this Datalog program is not definable in monadic second order logic. We look at a structure A that has as its domain the integers and the successor relation. We have already seen that the CSP of this structure A is the same as the yes instances of the Datalog program pi successor. Now it's easy to see that A and the disjoint union of A with itself satisfy the same first order sentences. For example, that every element has a successor and a predecessor. But clearly A and this disjoint union of two A's are not isomorphic. Therefore, the structure A is not omega categorical by definition. Now, even more, there also does not exist any other omega categorical structure B with the same CSP as A. This needs a short argument. But if we have this, we can apply the second result and get that the CSP of A, which is the same as the yes instances of the Datalog program pi successor, is not definable in monadic second order logic. Now we can put result 1 and result 2 together to achieve as an easy consequence a characterization of the intersection of MSO and Datalog. Recall what result 1 stated. For an arbitrary MSO sentence phi, where the class of finite models of phi is closed under inverse homomorphisms, we get that this class is a finite union of MSO definable CSPs. Result 2 stated that for a sentence phi, where the class of finite models is closed under disjoint unions and closed under inverse homomorphisms, that the class can be described as a CSP of an omega categorical structure. Now, we claim that every problem in the intersection of MSO and Datalog is the finite union of omega categorical CSPs. This means that every problem that on the one hand has a definition in MSO and on the other hand is the class of yes instances of a Datalog program can be seen as a finite union of omega categorical CSPs. Why does result 3 follow from result 1 and 2? If we have a problem in the intersection of MSO and Datalog, this problem is clearly closed under inverse homomorphisms by our observation about Datalog. Then result 1 implies that this problem is a finite union of MSO definable CSPs. But each of these MSO definable CSPs is of course itself closed under disjoint unions and closed under inverse homomorphisms. Therefore, by result 2, it is the CSP of an omega categorical structure. As I already mentioned in the introduction, one can generalize these results to an extension of monadic second order logic, called guarded second order logic. Guarded second order logic coincides with Courcell's MSO2 logic. And we have that result 1, result 2, and result 3 also hold for guarded second order logic. Let me mention some open problems. Rudolph and Knäuer introduced a logic called Monadic, which stands for nested monadic second order logic. They showed that this logic is contained in the intersection of MSO and Datalog. It is open if also the converse holds. The second question is, can the intersection of guarded second order logic and Datalog be described by some logic? So is there a logic that precisely captures this intersection?
Thanks for watching our video.